Okay, so question 4 is asking us to verify Stoke's theorem. Okay, so let's first learn about what Stoke's theorem is. So Stoke's theorem says that across the surface, if we were to calculate the curl of the vector field and find the flux of the curl, so the curl, remember, gives us a new vector field, so we want to find the flux of that new vector field across the surface, so that's a flux integral. Just now we got the curl of a vector field, which is still a vector field, is equal to the closed walk across the boundary of the surface of f dotted with dr. Okay, so the work done walking along the boundary of that surface. Okay, so imagine I've got some open surface here. Okay, so some open surface here. So this is my surface, S. Then if I was to walk around the rim in a positive direction, so positive is anti-clockwise, okay, will give me positive. That's my boundary of the surface, S. If I was to walk around that in a positive direction, it's equal to the curl of the vector field and the flux of that new vector field. Okay, so the curl of a vector field, remember, will just give me some new vector field. I'll call it G. So it's G dotted with n hat, which is the same as the flux integral we've seen before. So let's verify that. So the question's asking us to verify it. So we're going to work out the left-hand side and then the right-hand side. So let's start off working out the left-hand side. First thing is to find the curl of f. Okay, so it's equal to I, j, k, day x, day y, day z, and the vector field is x minus y all squared, 2z and x squared. Okay, so it's equal to I times day y of x squared, which is 0, and day minus day z of 2z, so that's minus 2. Then minus j, day x of x, which is 2x, minus day z of x minus y all squared, which is 0, plus k times day x of 2z minus day y of that. Okay, so minus day y of x minus y squared is 2 times x minus y times negative 1. Okay, because we've got the negative here. Okay, so that is my vector field. So it's going to be negative 2, negative 2x, and 0 minus minus, so it's 2x minus 2y. Okay, so negative there, so 2x minus 2y. So that is the vector field. Okay, so the next thing I need to do is find the surface, okay, the boundary, or n, okay, and the region on the xy plane that I'm integrating over. So it's z squared equals x squared plus y squared. So we know what that looks like. It's a cone. Okay, but unlike the previous question, this cone is going to be pointing downwards. Okay, it's going to look like this. That's what it's going to look like. Okay, so we're told S is the cone, z squared equals x squared plus y squared, that's that, with the plane z equals 2 as its boundary. So that's the plane z equals 2. So that is the boundary, day S, and that's the surface S. Okay, so we're going to be walking across that later. So for now, we've got a surface integral. We just need to find the region on the xy plane that it's over. Okay, the shadow, if you like, because that's my area A. So A, it's a circle. We're going to need polar coordinates, so we need to find limits on R and limits on theta. So theta is pretty easy. It's going all the way around from 0 to 2 pi. However, R, what's the maximum it goes out? Well, that's going to be when z is equal to 2. When z is equal to 2, I have 4 is equal to x squared plus y squared. So that's the circle. X squared plus y squared is equal to 4. So R is going to go from 0 to 2. Alright, so we're ready to integrate. Not quite. We need to find the normal vector, n. Alright, so we have to get all the z's, x, and y's on one side. But remember, you've got to be careful here because you need the direction in the z direction to be of positive 1. Okay, so we're going to have to write it like this. F is equal to, or I could write z is equal to the square root of x squared minus x squared plus y squared. And so f is equal to z minus square root of x squared plus y squared. Okay. Alright, so grad f is equal to negative x on the square root of x squared plus y squared to, positive y on the square root of x squared plus y squared and positive 1. Okay, so you need that positive 1 because, well, actually we've got a downward normal now, so this would be negative 1. So we need negative grad f. So our normal this time is going to equal negative grad f, which is equal to x on the square root of x squared plus y squared, negative y on the square root of x squared plus y squared, and negative 1. Okay, you can see here that we need the outward normal, so clearly it needs to be pointing down, so we need the negative 1. So now we're ready to find the curl of the vector field dotted with n. So that's equal to negative 2, negative 2x, 2x minus 2y, dotted with x on the square root of x squared plus y squared, negative y on the square root of x squared plus y squared, minus 1, which is equal to negative 2x square root of x squared plus y squared, plus 2y on the square root of x squared plus y squared, minus 2x plus 2y. So that's equal to, well, they add up nicely to give me 2y minus 2x on the square root of x squared plus y squared, minus 2y minus, plus 2y minus 2x. Okay, so I've got a 2y minus 2x on both of them, 2y minus 2x, and then I have a 1 on the square root of x squared plus y squared plus 1, which is equal to 2y minus 2x on 1 on the square root of x squared plus y squared plus 1. I'll leave it like that for now. Okay, so my flux, or my integral s of the curl of the vector field dotted with n hat ds is equal to, okay, my bounds on a, my bounds on a, which is 0 to 2 pi, 0 to 2, that which is 2y minus 2x times 1 on the square root of x squared plus y squared plus 1, and I need my r dr d theta, don't forget the Jacobian. So it's equal from 0 to 2 pi, 0 to 1. Okay, what's y equal to? It's equal to r sine theta minus 2r cos theta. Remember, x squared plus y squared is r squared, square root of that is r, so 1 on r plus 1, r d theta. So it's equal from 0 to 2 pi, 0 to 1, r times 1 on r plus 1 will give me 1 plus r. And I'm timesing that by everything there. So I'm going to get one of those, which is just going to be 2r sine theta minus 2r cos theta. And then I'm going to have plus r of them. So 2r squared sine theta minus 2r squared cos theta dr d theta. And now I can integrate that nicely. So it's from, I might swap the order of integration. So 0 to 1, 0 to 2 pi, factorize my sine thetas, so I've got 2r plus 2r squared of them, and factorize my cos thetas. Minus cos theta, and I've got 2r plus 2r squared of those as well, d theta dr. So it's equal from 0 to 2. Sorry, that should be a 2. I don't know why I've dropped the 2 somewhere. I think it's slowly just evolved into a 1. 0 to 2 pi. So I'm ready to integrate this with respect to theta. So sine theta goes to negative cos theta, 2r squared, and that goes to minus sine theta, 2r plus 2r squared, between theta equals 0 and theta equals 2 pi. dr. Okay, so you can actually work this out. If you sub in theta equals 2 pi to both of these, we're just going to get 0. So this is going to equal 0. Hence the integral from 0 to 2 of 0 dr is also 0. So the flux of the curl of this vector field across this cone is 0. So we've shown that the left hand side is equal to 0. Okay, so I would encourage you to go through and check that it's equal to 0, but I assure you when I sub in theta equal to 2 pi and theta equal to 0, this will just come to 0. So let's check that. Let's check that the work done by going along the rim of this cone is also equal to 0 in this vector field. Alright, so how do we find the work done? I need to come up with my parameterization r of t that gives me this curve. Okay, so it's a circle on the plane z equal to 2. So, and the radius is also at z equal to 2, it's 4. Remember, it's x squared plus y squared equal to 4. So I just have to parameterize that. So it's going to be 2 cos of t, 2 sine of t, and z is equal to 2. Okay, and it's going to go from t equals 0 to 2 pi. Okay, that's going to be the parameterization. That's going to give me the boundary of s. Day s is equal to r of t, 2 cos t, 2 sine t, and 2. Okay, so the work done, remember I need to find r dash of t. I'll use a different color. I need to find r dash of t, dr dt, is equal to negative 2 sine t. This is going to be 2 cos t. It's going to be 0. And I need to find r dash of t dotted with f, or f dotted with r dash of t, which is equal to f is x minus y all squared, 2z x squared, 2z x squared dotted with r dash of t, negative 2 sine t, 2 cos t, 0. Okay, so it's going to be equal to negative 2 x minus y all squared sine t plus 2z times 2 cos t plus 0. So the work done across my curve, so f dotted with dr, remember, goes from a to b. Okay, a to b, which is going to be my starting time and my ending time, which is 0 to 2 pi. F dotted with dr, which is this. So I've got negative 2 x minus y all squared sine t plus 2 or plus 4z cos t, okay, dt. Alright, so that's equal from 0 to 2 pi, and I have to sub in what x and y are and z. So it's equal to 2 cos t minus 2 sine t all squared sine t plus 4z, which is 2, so it's 8 cos t dt between 0 and 2 pi. So I just need to expand this out. 0 to 2 pi, negative 2 times 4 cos squared t. 2 times 2 is 4 times 2 is 8, so minus 8 cos t sine t plus 4 sine squared t times sine t plus 8 cos t dt, which is equal to 0 to 2 pi. I've got negative 2 yeah, negative 2, 4, because the 4 cos squared t plus 4 sine squared t is just going to give me 4, minus 8 cos t sine t plus 8 cos t dt, which is equal from 0 to 2 pi, negative 8 sine t plus 16 cos t sine squared t plus 8 cos t dt. Finally ready to integrate. So it goes from 0 to, so negative 8 sine t becomes sine cos negative sine negative sine goes to cos, so it's going to be 8 cos t. This is going to be plus 16 on 3 sine cubed t plus cos goes to sine 8 sine t from 0 to 2 pi, which again, if you sub that in, I assure you, you're going to get 0. Okay, so we've shown that the right hand side, the work done along the boundary of S. Okay, so just a couple of quick mentions of that. You're just parameterizing the boundary and making sure we're going in a positive clockwise direction. So t0 to 2 pi. Okay, so be careful with that. Yeah, just be careful when you're finding the boundary. Remember what we're doing here. We're finding work done. So go back to your notes. You need to parameterize the curve and then dot it with the vector field, or dot the derivative of it with the vector field, and then calculate the integral. So go revise that. But we have verified the question. We have verified Stokes' theorem by showing that it's both equal to 0. So have a go at question 4b, and have a look at the next video just talking about this week's quiz and a couple of other announcements.